Welcome! In this session, we'll explore an interesting problem titled Number of Submatrices that Sum to Target. This problem challenges us to efficiently calculate the number of submatrices in a given matrix that sum up to a specific target value. We'll start by discussing the brute force approach and then explore optimized methods to solve it. Let's dive in. This problem asks us to determine how many submatrices of a given 2D array have a sum equal to a specific target. A submatrix is essentially a rectangular portion of the matrix, consisting of contiguous elements. The input includes the matrix itself, represented as a list of lists of integers, and the target value, which is the sum we are looking for. The output will be a single integer, indicating the count of all such submatrices that sum to the target. For example, if the input matrix is a 2x2 array and the target is 0, we are tasked with identifying all contiguous submatrices within this matrix whose elements add up to exactly 0. Let's explore some examples to clarify this further. In the first example, the input matrix is a 2x2 array, 1, -1, -1, 1, and the target is 0. The output is 5 because there are 5 submatrices in this case that meet the condition. These include 3 1x1 submatrices at specific positions, such as matrix 0, 1, and matrix 1, 0, each summing to -1, and matrix 1, 1, which sums to 1. Additionally, there is a 2x1 submatrix formed by the first column, which sums to 0, and the entire 2x2 matrix itself, which also sums to 0. Together, these give us a total of 5 submatrices. In a second example, with the matrix 0, 1, 1, 0, and a target of 1, the output is 4. Here, there are 4 submatrices that sum to 1, including 3 individual 1x1 submatrices, such as matrix 0, 1, and matrix 1, 0, and 1 2x1 submatrix consisting of the second column. Now, consider the third example, where the matrix is a larger 3x3 array 1, 2, 3, 4, 5, 6, 7, 8, 9, and the target is 12. The output is 4, as there are 4 submatrices that sum to 12. These include the top left 1x3 submatrix, formed by the first row 1, 2, 3, and the middle 1x3 submatrix, which is the second row 4, 5, 6. Additionally, we can identify 2 2x2 submatrices. The first is the top left 2x2 submatrix, consisting of elements 1, 2, 4, 5, and the second is the bottom right 2x2 submatrix, with elements 5, 6, 8, 9. Together, these cases provide us with a total of 4 submatrices that meet the condition. This problem comes with important constraints and edge cases to consider. The matrix dimensions, m and n, can go up to 100, meaning the maximum size of the matrix is 10,000 elements. The values in the matrix can range from -1000 to 1000, allowing for negative, 0, or positive elements. The target sum can also be a large positive or negative number, ranging from -10 million to 10 million. Some notable edge cases include matrices with only one row or one column, where the problem simplifies to finding subarrays with a sum equal to the target. Another scenario is when the matrix contains only zeros, which can result in a large number of solutions if the target is 0. Additionally, the presence of negative values introduces the possibility of sums decreasing as elements are added. Because of the large matrix dimensions and wide range of values, an efficient algorithm is crucial to avoid excessive computation and ensure that the solution is performant within the given constraints. To start, let's consider the brute force approach. The main idea here is to iterate over all possible submatrices in the given matrix. For each submatrix, we calculate its sum and then check if it matches the target value. This involves iterating over all pairs of top left and bottom right corners to define the submatrices, which is quite straightforward to implement. However, this simplicity comes at the cost of efficiency. Since there are roughly open parenthesis m times n close parenthesis squared submatrices for an mxn matrix, and calculating the sum of each submatrix could take up to m asterisk n operations, the overall time complexity becomes open parenthesis m times n close parenthesis cubed. This makes the brute force approach impractical for large matrices. While it's a good starting point to understand the problem, it's far too slow to use in competitive programming scenarios or with large input sizes. Now, let's look at the optimized approach that uses prefix sums and hash maps. The key insight here is that calculating the sum of all elements within a submatrix repeatedly is redundant.
Instead, we use prefix sums to compute submatrix sums more efficiently, avoiding recalculations.
The breakthrough is recognizing that we can treat each row as a one-dimensional array and reduce the problem to finding subarrays whose sums equal the target, which is a known problem solvable with hash maps.
Here's the approach. First, we iterate over all pairs of rows to define the top and bottom boundaries of the submatrices.
For each row pair, we compute the prefix sum of each column within the current range. This reduces the matrix to a compressed 1D array of column sums. We then use a hash map to track cumulative sums and their frequencies, allowing us to find subarrays that match the target efficiently.
The result is a significant reduction in complexity.
The outer loop iterating over row pairs runs in O, m squared, the inner loop over columns with prefix sum calculations takes O, n, and using the hash map for subarray sums also takes O, n. Combining these, the overall time complexity becomes O, m squared asterisk n. This optimized approach comes with several trade-offs. On the positive side, it is significantly faster than the brute force method, making it well suited for larger matrices. It does require additional space to store the hash map, but the space complexity is manageable at O, n, which is proportional to the number of columns. However, the implementation is slightly more complex due to the use of prefix sums in hash maps. Beyond this, other alternatives were considered but found less suitable. A divide-and-conquer approach, for example, recursively subdivides the matrix, but its complexity of O, m asterisk n, asterisk log, m asterisk n, and implementation overhead make it less appealing. Another alternative, using a 4D dynamic programming table to store submatrix sums, has a complexity of O, m squared asterisk n squared, which is impractical due to the massive space requirements. While these methods have their merits, they fall short in terms of efficiency and usability for this specific problem. Ultimately, the chosen strategy is the optimized approach that combines prefix sums with hash maps. This method strikes the right balance between time and space complexity, achieving O, m squared asterisk n, for time and O, n, for space. By leveraging hash maps to eliminate redundant computations, it ensures the solution remains efficient even for larger matrices. Additionally, this approach is highly scalable, making it an excellent choice for competitive programming. It also generalizes well to other related problems, such as finding subarray sums in one-dimensional arrays, which adds to its versatility. By avoiding the inefficiencies of brute force, the complexity of divide and conquer, and the impractical space usage of 4D dynamic programming, this strategy provides a clean, robust, and efficient solution that is relatively easy to understand and implement. To solve this problem, we need to determine how many submatrices in a given 2D matrix sum up to a specified target value. For example, consider the matrix shown here. A submatrix is any rectangular portion of the matrix defined by its top left and bottom right corners, and our task is to evaluate all possible submatrices within this matrix to check if their sum equals the target. While it's possible to solve this using a simple brute force approach by iterating through all potential submatrices and summing their elements, this method is computationally expensive. It involves multiple nested loops, making it impractical for larger matrices. Therefore, we need a more efficient strategy, which we'll explore using prefix sums and hashing. The brute force approach involves iterating over all possible pairs of top left and bottom right corners for each submatrix. For each pair, we calculate the sum of all elements within the submatrix by iterating through its rows and columns. While this method is conceptually simple, its time complexity is O, n to the power of 4, for an nxn matrix, due to the 4 nested loops required. This level of complexity is prohibitive for larger matrices and doesn't scale well. To improve efficiency, we can use an optimized approach that combines prefix sums and hashing. The key idea is to pre-compute sums to avoid redundant calculations and leverage a hash map to quickly identify submatrices that match the target sum. The optimized approach begins by pre-computing prefix sums for each row. This allows us to calculate subarray sums in constant time after pre-computation. For instance, a row like 1, 2, -1 will have prefix sums 1, 3, 2. Next, we fix two rows to define the top and bottom boundaries of our submatrix. By summing the columns between these rows, we effectively reduce the 2D submatrix sum problem into a simpler 1D subarray sum problem. At this stage, we use a hash map to store cumulative sums of the 1D array. For each column, we compute a running sum and check if the difference between this running sum and the target exists in the hash map. If it does, it implies that there's a submatrix whose sum equals the target. Finally, we update the hash map with the current running sum to continue tracking subarrays. Using this approach, we can leverage prefix sums and hash maps to significantly reduce the time complexity. Prefix sums allow for constant time subarray sum calculations after pre-computation, while the hash map enables efficient lookups for cumulative sums, avoiding the need for nested loops. By breaking the 2D problem into a 1D problem, we simplify the computation while maintaining correctness. In terms of complexity, this method has a time complexity of n cubed, 2 loops for fixing rows and 1 loop for iterating over columns, while the hash map operations are constant time on average. The space complexity is n, due to the hash map and prefix sum array. Additionally, the algorithm handles edge cases like negative numbers, empty matrices, and scenarios where no submatrix matches the target, making it robust and versatile for a wide range of inputs. Here, we start by importing the default dict from Python's collections module, which will help us efficiently manage prefix sums later on. Within the solution class, the number submatrix sumTarget method is defined to solve the problem. First, we determine the dimensions of the matrix by retrieving the number of rows and columns. Next, we pre-compute the prefix sums for each row to prepare for efficient submatrix sum calculations. This is done by iterating over each row and updating each column to include the sum of all previous columns in that row. This transformation allows us to quickly calculate the sum of any subarray within a row. After initializing a variable result to store the count of submatrices meeting the target sum, we proceed to iterate over all possible pairs of columns, which will define the vertical boundaries of the submatrices we are considering. For each pair of columns, we use a default dict to track the prefix sums of the submatrix sums as we process each row. This hash map is initialized with a key value pair of 0 mapping to 1, accounting for the scenario where the current sum directly equals the target. Within the nested loops, we calculate the cumulative sum for submatrices spanning the current column range across rows. For each row, the sum is updated by subtracting the prefix sum up to the column before call_start from the prefix sum at call_end. This gives the sum of elements in the desired column range for the current row. To check if a submatrix sum equals the target, we verify if cur_sum target exists in the prefix sums hash map. If it does, it means there is a submatrix whose sum equals the target, and we increment the result by the count of such prefix sums. After this check, the current sum is added to the prefix sums hash map, ensuring we account for it in subsequent calculations. Once all rows and column ranges are processed, the method returns the total count of submatrices that meet the target sum. Here, we begin by importing the necessary packages and defining our solution class. The method number submatrix sumTarget takes a 2D matrix and a target value as input. First, we calculate the number of rows and columns in the matrix. Then, to make the submatrix sum calculations more efficient, we pre-compute the prefix sums for each row. This is done by iterating through the rows and updating each cell to include the cumulative sum of all elements to its left. Next, we initialize a variable, result, to store the count of submatrices that sum to the target. The next step involves iterating over all possible pairs of columns, which are defined by the variables callStart and callEnd. For each pair, we use a hash map to store prefix sums encountered so far. This helps us quickly check if a submatrix with the required sum exists. We initialize the hash map with a base case, where the prefix sum of 0 has a count of 1. Now, we iterate through each row to calculate the sum of elements between the two columns for the current row. Here, we calculate the sum of elements between the columns callStart and callEnd for the current row. This is done using the pre-computed prefix sums. If callStart is greater than 0, we subtract the prefix sum up to the column before callStart to get the correct range. Once we have the current sum, we check if the difference between the current sum and the target exists in the hash map. If it does, this means we have found submatrices that sum to the target, and we add their count from the hash map to our result. After this check, we update the hash map with the current sum, incrementing its count. This ensures that the hash map remains up to date for subsequent rows. The process continues for all rows within the current column range, and then for all possible column pairs. Finally, we return the result, which holds the total count of submatrices that sum to the target. To solve this problem, we start with a simple example. The input matrix is a 3x3 grid, and the target sum is 12. The first step is to pre-compute row prefix sums. This means that for each row, we calculate cumulative sums from left to right. For example, in the first row, the values transform from 1, 2, 3 to 1, 3, 6, where each number represents the sum of all elements from the start of the row up to that point. Applying this to all rows, the matrix becomes 1, 3, 6, 4, 9, 15, 7, 15, 24. This transformation allows us to later compute submatrix sums efficiently by subtracting prefix sums. Next, we iterate over all possible column pairs. For a given pair of columns, we treat the area between them as a one-dimensional array of sums for each row. To speed up the computation, we use a hash map to store prefix sums for these row ranges, which helps us quickly identify submatrices that match the target sum. Now, let's consider the column pair where both start and end at column 0. We initialize a hash map, prefix_sums, with a default entry, 0, 1, and set the current sum to 0. For each row, we calculate the cumulative sum within this column. In row 0, the cumulative sum becomes 1. At this point, we check if the difference between the current sum and the target, which is -11, exists in the hash map. Since it does not, we update the hash map to include the new cumulative sum, resulting in 0, 1, 1, 1. In row 1, the cumulative sum becomes 5, and again, there is no match for the difference -7. The hash map is updated to 0, 1, 1, 1, 5, 1. Finally, in row 2, the cumulative sum reaches 12, and this time, the difference between 12 and the target, which is 0, exists in the hash map. This means we found a submatrix matching the target, so we increment the result to 1. Next, for the column pair, 0, 1, we reset the hash map and repeat a similar process. By following this logic for all column pairs, we find that the total number of submatrices that sum to the target is 4. In this example, we explore an edge case with negative numbers. The matrix is a 2x2 grid, and the target sum is 0. First, we pre-compute row prefix sums. In this case, the transformation results in 1, 0, 1, 0. This transformation ensures that we can efficiently calculate the sum of any submatrix using prefix sums. Now, we iterate over all column pairs. For the column pair, 0, 0, we initialize prefix_sums with 0, 1. As we traverse each row, we update the cumulative sum and check if the difference between the current sum and the target exists in the hash map. For example, in row 0, the cumulative sum becomes 1, and we update the hash map accordingly. In row 1, the cumulative sum changes, and we continue checking and updating. Using this process for all column pairs, we calculate that the total number of submatrices matching the target is 4. This example demonstrates the solution on a single row matrix, where the input is 1, 2, 3, 4, and the target sum is 6. First, we pre-compute the row prefix sums, transforming the row into 1, 3, 6, 10. This step allows us to compute any range sum within the row efficiently. Next, we iterate over all possible column pairs. For a given pair of columns, we calculate the sum of the subarray between these columns. Using the same approach as before, we use a hash map to track the cumulative sums and quickly identify subarrays that match the target. By processing the single row in this manner, we find that there are 2 subarrays that sum to the target, giving us a final result of 2. To summarize, this solution relies on 2 key insights. First, pre-computing prefix sums enables efficient calculation of submatrix sums by reducing the need for repetitive summation. Second, using hash maps to store running sums allows us to quickly determine whether submatrices with the target sum exist, leveraging the difference between the current cumulative sum and the target. By iterating over all possible column pairs, we ensure that every potential submatrix is considered, making this approach both comprehensive and efficient. These techniques together provide an effective strategy for solving the problem. To understand the time complexity of our solution, let's break it down into its key components. First, we pre-compute the row-wise prefix sums. This involves iterating over each row and calculating cumulative sums for all columns in that row. Since we process every cell of the matrix exactly once during this step, it requires rows asterisk calls time, where rows refers to the number of rows and calls refers to the number of columns in the matrix. Next, we look at how we iterate over pairs of column boundaries. Using two nested loops, we generate all possible pairs of columns, which amounts to calls asterisk, calls plus 1, / 2 pairs. This simplifies to calls caret 2. Finally, for each column pair, we calculate the sums of submatrices that span these columns. This involves iterating over all rows for each column pair, which takes rows. When you combine this with the calls caret 2 column pairs, this step contributes rows asterisk calls caret 2 to the overall time complexity.
Now let's consider the hash map operations during the computation.
As we calculate submatrix sums for each column pair, we use a hash map to check for previously seen prefix sums and update it as necessary. Hash map operations, such as lookups and updates, are on average due to efficient hashing. These operations occur for every row in a column pair, but since they're included in the rows asterisk calls caret 2 term derived earlier, they don't add any additional complexity. Combining all these steps, the total time complexity becomes rows asterisk calls plus rows asterisk calls caret 2. However, the rows asterisk calls caret 2 term dominates for larger matrices, so the final time complexity simplifies to rows asterisk calls caret 2.
Let's shift our focus to space complexity. First, consider the space required for prefix sums. These are computed in place within the input matrix, so no extra memory is needed for this step. Next, we have the hash map, which stores prefix sums encountered while iterating through the rows for a specific column pair. In the worst case, the number of unique cumulative sums stored in the hash map is equal to the number of rows, which results in rows, additional space. Since there are no other significant space requirements, the overall space complexity is dominated by the hash map, making it rows. This is a significant improvement compared to more naive approaches that might require storing all possible submatrix sums. When we compare the optimized approach to a brute force solution, the improvements become clear. A naive method would involve iterating over all possible submatrices directly, calculating their sums, and checking if the result matches the target. The total number of submatrices in the matrix is rows caret 2 asterisk calls caret 2, and calculating the sum of each submatrix could take rows asterisk calls in the worst case. This leads to a staggering time complexity of rows caret 3 asterisk calls caret 3. In contrast, the optimized approach leverages prefix sums and hash maps to reduce the time complexity to rows asterisk calls caret 2. The space complexity is also drastically reduced, as the optimized solution only requires rows, additional space for the hash map, compared to the brute force method, which could require much more space to store intermediate results. Finally, let's analyze the best, average, and worst case scenarios for this algorithm. In the best case, the matrix is small, and the number of unique cumulative sums encountered is minimal. While the time complexity remains rows asterisk calls caret 2, the hash map operations are faster because fewer entries are stored. In the average case, hash map operations remain efficient, and once again, rows asterisk calls caret 2 dominates the runtime. In the worst case, the matrix is large, and most cumulative sums are unique, which could slightly increase the memory overhead for the hash map. However, even in this scenario, the overall complexity is still rows asterisk calls caret 2. Mathematically, the calls caret 2 term comes from the number of column pairs, which is approximately calls asterisk calls plus 1 / 2. For each column pair, we perform rows operations, leading to the final complexity of rows asterisk calls caret 2. Hash map operations are efficient on average, ensuring that this approach outperforms brute force methods significantly. When solving this problem, there are a few common pitfalls to watch out for. One of the most frequent mistakes is implementing an inefficient brute force solution. Calculating the sum of each submatrix repeatedly within nested loops can quickly lead to excessive time complexity. For example, iterating over all submatrices of an MXN matrix results in m squared asterisk n squared operations, which becomes impractical for larger matrices. A straightforward fix is to use prefix sums or other pre-computed values to eliminate redundant calculations. Another common issue is neglecting edge cases.
It's important to account for scenarios like empty matrices, matrices with a single row or column, or matrices where all values are negative. Testing your solution against these cases ensures robustness. Finally, misusing prefix sums is another frequent error. For instance, if you don't correctly account for overlapping regions when deriving the sum of a submatrix, your results will be incorrect. The key here is to carefully manage inclusion and exclusion when applying the prefix sum technique. Now, let's address two additional pitfalls. If the matrix is sparse, meaning it contains many zeros, treating it like a dense matrix is inefficient and wastes computational resources. A more optimized approach might involve using a hash map to store only non-zero values, which can significantly improve performance in such cases. Another common issue, particularly in languages like Java or C++, is overlooking integer overflow. When summing large submatrices, the result could exceed the maximum allowable value for standard integer types, especially if the matrix contains very large positive or negative numbers. To prevent this, you can use data types with higher capacity, such as long in Java, or implement modular arithmetic where necessary. These adjustments help ensure your solution is both efficient and robust. Understanding how to approach problems like this in an interview setting is also crucial. Pre-computations, such as prefix sums or difference arrays, are often the foundation for efficient solutions. These data structures allow you to query sums or ranges in constant time, which is invaluable in reducing complexity. It's also important to optimize based on the given constraints. For smaller matrices, brute force might be sufficient, but for larger inputs, techniques like prefix sums or even Cadon's algorithm for 2D arrays become essential. Be prepared for interviewers to introduce slight variations to the problem. For instance, they might ask you to find the maximum submatrix sum instead of targeting a specific value. Adaptability is key. Additionally, always explain your optimizations clearly. Demonstrating why you chose a specific approach and how it improves performance over brute force shows a deep understanding of algorithm design and trade-offs. There are several related problems that can help you deepen your understanding of this topic. LeetCode 560, subarray sum equals k, is a 1D version of this problem that introduces the use of prefix sums and hash maps for optimizing subarray sum calculations. LeetCode 363, max sum of rectangle no larger than k, is a more challenging variation where you need to find the maximum sum of a submatrix while meeting specific constraints. LeetCode 304, range sum query 2D immutable, focuses on pre-computing a prefix sum matrix to enable efficient range queries. Finally, there's LeetCode 85, maximal rectangle, which involves finding the largest rectangle of ones in a binary matrix using dynamic programming and matrix traversal techniques. Each of these problems builds on similar concepts, allowing you to practice and refine your approach for solving matrix-related challenges. Lastly, it's worth exploring alternative approaches and understanding their trade-offs. The prefix sum approach, for instance, is highly effective in reducing the time complexity of submatrix sum calculations from m squared asterisk n squared to m asterisk n. However, it does require additional space to store the prefix sum matrix. Cadon's algorithm for 2D matrices is another option, particularly useful for finding the maximum submatrix sum. It applies the 1D Cadon's algorithm within specific row ranges, offering a highly efficient solution, but it's more complex to implement and isn't suited for problems requiring exact target sums. Finally, using a hash map in combination with prefix sums is great for optimizing problems that involve specific target sums, like submatrix sum equals k. The downside is the added overhead of managing the hash map and the potential for collisions in edge cases. Choosing the right approach depends on the problem requirements and constraints, but knowing these alternatives gives you flexibility and a deeper understanding of the trade-offs involved. Great job! We've summarized the key concepts and takeaways from the problem number of submatrices that sum to target. Remember the importance of prefix sums and hash maps in solving matrix-related problems efficiently. Thank you for joining, and we hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!